Hi, in this session, we will explore data processing part 3, a crucial phase in preparing data for effective machine learning and analytics. Before we apply any model, it is essential to clean, standardize, and transform the data to ensure consistency and reliability. Today's focus will be on the key processing techniques: data normalization, min-max scaling, z-score, and text normalization. Transform data to consist scale numeric features via min-max or z-score and text normalization, enabling fair comparison across attributes. Proxy matters, similarity, dissimilarity, and coherence captures how alike our different data points are, forming the foundation for clustering, classification, and recommendation systems. Binary data, binary distance matrix, symmetric, asymmetric, and Jaccard coefficient. Data binning representation using mean and boundary. Reduce data complexity by grouping values into bins and replacing them with either the mean or the nearest boundary. Adding in smooth and discretization. Proper pre-processing ensure data is comparable, clean, and ready for analysis, leading to better predictions. Plus, we will include code outputs and visual explanation. By the end, you will understand how to apply these techniques effectively to enhance your models. Let's get started. Normalization, data normalization. Data normalization. Normalization is the process of adjusting the values in a dataset to a common scale without distorting differences in the range of values. The goal is to prevent features with large range from dominating others, ensuring equal contribution from all features. Data rating differences. Features in a dataset often they have vastly different scales. For example, comparing feature like age ranging 0 to 100 and income ranging 10,000 to 2 lakh. If left unnormalized, income will dominate model training due to its larger numerical range. Importance in machine learning: algorithms like k-nearest neighbors, KNN, support vector machines, SVM, and neural networks are sensitive to scale of the data. These algorithms use distance metrics or gradients which are heavily impacted by the differences in a future scale. Importance on model coverage. When features have different scales, model may converge slowly or inefficient, leading to longer training times and potentially suboptimal performance. Why is normalization important? Without normalization, feature with larger range can dominate the model's prediction, leading to bias in favor of those features. Feature contribution, just like consider a scenario with a feature like height in centimeter and income in dollars. The large scale of income may cause the model to overlook height because the range of income is significantly higher. Improve model training by bridging all the features onto similar scale. Normalization helps improve the model's training efficiency and convergence. Like say efficiency increase with normalized data, algorithm can train faster and converge more quickly because the model treats all feature equally. Types of normalization techniques. Normalization ensure that features with different units and scales do not dominate machine learning models. There are two popular methods. Min-max scaling. This method transfers the data into a fixed range, typically 0, 1. Z-score standardization. This method rescale the data by subtracting the means and dividing by the standard deviation, producing data with a mean of 0 and a standard deviation of 1. Min-max normalization. Min-max normalization. Min-max normalization is uh, data by scaling into a defined range 0, 1, or sometime if required 1 minus 1. This is a particularly useful for algorithms that require standardized output values such as neural network and decision tree. One key advantage is that it preserves the original relationship between data point. However, its main drawback is sensitive to outliers. A single extreme value can disproportionately shrink the rest of data. For example, imagine test score range from 50 to 100. After mean max normalization, 50 maps to 0, 0 and 100 is maximum is 1. A score like 75 would be mapped to 0.5. This allows machine learning model to process the value efficiently. This is a code. So we have a sample data and then initialize and normalization for min max, and that is a plotting area, and then create a figure, plot original data points, and then normalize the points and contact proceeding points. So this is the graph. The blue point is represent to the original data values. The red point the normalized data values after applying min max scaling. The dashed lines show how each original values map into the normalized counterpart. The transformation ensured the minimum values 20 is mapped to 0 and maximum value 100 is mapped to 1. Min-max normalization is particularly useful in machine learning models, especially for neural networks where input values should be in a fixed range. And that is the manual results. Z-score normalization. Z-score normalization, original feature values, and then this is the mean feature values and standard deviations of the feature values. Characteristics center data around 0 mean is equal the scale it based on standard deviation. Useful when features are different units are range. Uh, Retains outlier influence unlike mean max normalization. Z-score normalization, also called standardization, transform the data so that its means become 0 and standard deviation become 1. This technique is particularly useful when the data set contains features with different units of measurements, height in centimeter versus height in kilogram, weight in kilogram. The algorithm assumes a Gaussian distribution, a linear regression, PSA, and clustering. There are outliers, but they should not heavily influence scaling. Unlike mean max scaling, z-score does not constrain value within a fixed range, but instead center them around 0. Z z-score normalization code initialize standards scales to apply z-score and then plot the distributions. Z-score graph, each blue dot represent a data point from the original list, like 20, 50, 80 and 100, and this line is from here. So the horizontal red shades line is mean of data, that is 0. The distance of each point from the center shows how far in which direction a value from the average. Left the red line below average and right line is the above the average. So let's say the 50 is minus 0.28 is goes from here, and then gradually everyone is taking this side. Mean max scaling versus z-score normalization. Mean max scaling versus v-score normalizations. The features are range difference. Mean max scaling transform values into a fixed range, typically 0 to 1, which is useful when you bounded values. Z-score normalization center data around 0, making it useful for algorithms that assume normal distribution. Outlier sensitivity. Main scale scaling is highly sensitive to outlier because extreme values shift the range. If there is a very large or small value, that is compressed most of the data into a small species. Z-score is normalization reduces the impact of outlier because it is standardized based on a standard deviation, ensuring a more balanced spread. When to use min max scaling? When you know the minimum and maximum values in advance, or when data needs to be a specific range pixel intensity in images processing. Z-score normalization when data has different scale, when the algorithm assumes normally distributed linear regression or PCA. The best for min max is commonly used in deep learning, KNN, and deep learning and model that rely on distance-based measures. Z-score work well for linear regression, PSA, and SVM. And this is a graph original data set in left side. This is a graph shows raw data sets before applying any scaling. The values range 10 to 100, which extreme outlier are 300. This one. Each data point is labeled, making it easier to track specific values. Most values are relatively close together. The outlier is far away from the rest of the data. Mean max scale data transform value between 0 and 1. The smallest value is 10 and becomes 0, whereas the largest value 300 become a 1. Key observation: the outlier of 300 is a scale to 1. This 300 scale to 1, while most values shrink closer to 0. This can distort the distribution because outlier heavily influence scaling. The spacing between value is not preserved when it was the original data. Z-score normalization center around 0 with the standard deviation of 1. Most values key close to 0, while the outlier 300 is far above the rest. Unlike min-max scaling, the relative spacing between values is preserved. Outliers don't compress under other values, making this method better for dataset with extreme values. Code output and visual explanations. Min-max normalization. Here we have used min-max scaling for simple dataset. Original values are 10, 20, 30, 40, 50. The output transform the smallest values is 10 and 0 and the largest is 50. All immediate values are scaled proportionally between these two twos. And this scaling keep the relative spacing between data points impact the graph of this would be straight linear transformation of the input compressed into a 0-1 range. This method is especially useful when working with models that are sensitive to input magnitude like neural network. Z-score normalization. In contrast, Z-score normalization transforms the same datasets into value based on how many standard deviation each point is from the mean. The mean of this data is 30. and the standard deviation approximately is 15.81. So 10 is roughly 1.2 standard deviation below the mean, while is 50 is 1.26. On a graph, this would appear centered around 0 with the symmetric spacing on other side. Ideal for algorithm that assumes a distribution on rely on distance. Mean max versus z-score normalization. Basic concepts: mean max transform feature to a fixed range, especially 0 to 1. Normalization, on the other hand, standardized data bias in centering around 0 and scaling use standard deviation. This difference significantly affects how algorithms interpret feature magnitudes. Sensitivity, high sensitive mean max is very sensitive to outlier. A single extreme value can squash the rest of the value into a tight cluster. In contrast, Z score is more robust and treat outlier more gracefully since it's based on the spread of data rather than fixed boundaries. Examples are, for example, imagine house prices. If one house costs $1 million while most are 100K and 300K, mean max will compress the values too much. With z-score, a 1 million score house would still show on extreme but would not ruin the spread of others. Similarly, with exam score, z-score helps in highlights outlier without distorting everything else. Best use for KNN, use min-max when model require input to be in a limited range like neural network or image processing tasks where pixel values range from 0 to 255. Z-score works better than the model depends on distance or assume a distribution like PCA and SVM. Ideal scenarios, if your data set is well behaved with no extreme outlier, min max will do just fine. But when data is skewed or varied significantly, Z score retain meaningful distance and pattern, making it better choice. Key decision guide. If model are require bounded inputs, you are working in the clean uniform data, go with maximum scaling. Ask yourself if model require bounded input. If yes, min max does the data have outlier or need to follow a normal distribution. Then go with z square also for clustering and nearest neighbor algorithm. Z score is useful more effectively. Quick decision guides. Need values min max. If your algorithm is modeled dataset strictly between 0 and 1, like a neural network or image pixel data, min max scaling is the ideal method. It keeps all data within a fixed range, which can be crucial when activation functions are bounded like segment or time. Presence of outliers, min max scaling can be heavily skewed by outlier. If you have an 2 or extreme values, the entire scale get compressed. Z-score handles its better standardization based on mean and standard deviation, making outlier more monographable without distorting the rest of the data. Distance-based model, KNN, SVM, that is core normalization. Models like KNN and SVM rely on calculating distance between data points. If features are not scaled, one feature might dominate the others. Z-score ensure all features contribute equally by bridging the same scale centered around 0 and scale by variance. Normal distribution assumptions, Z-score normalization. Again, some algorithms like linear regression, PCA, and naive Bayes assume the input features are normally distributed. Z-score helps meet this assumption by shaping the data to a bell curve structure centered around way which enhance performance and accuracy. Thank you. Text normalization, and these are subtopics. Text normalization. These are almost more than 20s. Normalization. Why is text normalization important? Before we can apply any algorithm on text data, we must first prepare and clean that data. Text normalization is the first step in that preparation. Text data often comes from multiple sources, web pages, social media, chats, each using different formats, spelling, or symbols. Text normalization helps convert all of this into a standard format so that the machine learning models can interpret the data more accurately. Without normalization, the data can be noisy, full of inconsistent capitalization, punctuation, or slang. This noise affects the accuracy of NLP models. By reducing this noise, we help algorithms focus on meaningful patterns instead of irrelevant differences. In NLP applications like chatbots, sentiment analysis, or topic extraction, normalization ensure that similar words and phrases are treated as equivalent. This increases both efficiency and accuracy in processing natural language data. Converting to lowercase. Converting all character to lowercase, one of the first step in text normalization. The step ensure hello word, hello and hello are treated as the same word by machine learning models and text analysis tools. Text data can be inconsistent in casing due to user input, formatting, or system source. By applying lower, we standardize the text, improved token matching, reduce redundancy in the vocabulary, support efficient pre-processing for NLP tasks like sentiment analysis or search. Removal of URL. URL is the data rarely contribute meaningful insight during text analysis unless we are study links directly. In NLP tasks like sentiment analysis, topic modeling, or classification, URL act as a noise. The regular expression matches any substring that start with HTTP or www, followed by a non-white space character. It helps in removing most common URL format. These steps simplify the text and improve the performance of downstream tasks. Removal of HTML tags. When scraping text from the website, we often get HTML like a division, span, etc. These tags do not carry semantic meaning in NLP task and need to be removed. Beautiful Soap is a Python library of parsing HTML, XML documents. The method .get underscore text exactly only the visible user friendly content from the HTML. The process ensures the only meaningful text is retained improving data quality for analysis. Removal of URL versus removal of HTML tags. Removal of HTML, first we see strip out actual links HTTP that often clutter text data. Focus on cleaning links from tweets, email, and messages using regress to match, remove, and pattern that begin with HTTP or www helps eliminate external link noise. So removal of HTML tags, clean up markup languages like add division when text come from website, focus on structured tags around contents, use beautiful soap or extract only visible text, ensure readable text for raw data pages. While both steps remove the text, we don't want URL or actual links like HTTP or HTML tag are part of the web code. We need to remove both of different reasons. One of the cleaning user post, the other one scraping from websites. Removing numbers. Eliminate digits number. Numbers can carry meaning in some context. E.g. dates, price, quantities. However, in many NLP tasks, especially sentiment analysis, emotion detections, or topic modelings, numbers often do not provide semantic values. Removing numbers help reduce noise in text, simplify token focus analysis on words and contexts. Convert number to words. Converts numeric digit into textual representation, works for integrates, decimals, and even currencies with configurations. Instead of removing numbers entirely, we can convert them to words, especially when quantities matter, 2 days or 5 hours. This approach is useful for financial, medical, or logistic text, where numbers contributes to meanings. Apply spelling corrections. Spelling error, especially in informal content, can lead to vocabulary fragmentation in NLP tasks. Using the autocorrect library helps clean this noise. Work with both individual words and entire sentences, great for handling common errors in English typos. Converted characters to ASCII codes. Removal asking from the characters in multilingual data set, especially from European, Latin America, or African sources. ASCII characters are common example like E, Cafe, Nino. These characters may cause inconsistent matching during tokenization. The Unicode library convert Unicode characters. Converting chat words to normal words. In casual communication, users often abbreviate words to save time, especially in text, tweets, WhatsApp, etc. A custom dictionary mapping is used to translate chat abbreviation into formal English. Why this matter? Improve accuracy in sentiment analysis, intent detections, and text classification. Reduce semantic ambiguity and increase vocabulary consistencies. So, by the way, you and are expanding contraction, convert in contraction into expanded form, can't or is. Constructs are common in spoken and informal written English like don't, isn't, we are, I have. While human easily understand contractions, NLP model not. Expanding contraction reduce lexical diversity, artificial caused by alternative forms. Makers text more standardized, which help downstream NLP tasks. The contraction library use these are built-in libraries safely and accurately expanded common contractors. So I can't move to I cannot. It it is. Stemming reduces words in base root forms like this one. Stemming is particularly useful in information retrieval, text classification, and search engines, where semantic accuracy is less important than pattern recognition. Most common stemmer portal stemmers from NLTK. It is fast but not always linguistically correct. Use stemming when speed is more critical than accuracy. Working with large corpora for clustering or classification for higher accuracy, consider lemmatization, which return valid dictionary words. So running, runner, runs. Lemmatization reduces words into their base dictionary forms. Part of speech is a like stemming but smarter. It uses the part of speech and grammar rules to return the correct dictionary from a word. For example, better is not just chopped, it is interpreted as an adjective and mapped to good. It is powered by a WordNet, a lexical database of English, while stemming might turn running into run. It could also turn universe into universe. A non-word lemmatization ensures that every result is real word. Context matter, making it deals for tasks where grammar or meaning is important, like questions answering or chatbots. So here, better, good. Removal of emojis. Emojis can be removed or converted. Emojis are modern language elements that convey emotions, tone, and context. In social media or informal text, they are common, but for many NLP tasks like topic modeling, name entity, recognize text classification, non-text sentiments, they introduce noise. In this example, first we convert emojis into descriptive forms, smiling face with smiling eyes. Then we use a regular expression to remove those emojis words from the text. This helps standardize the text for machine learning models that are not trained to interpret emojis. But in some use cases like sentiment analysis, converting emojis into meaningful words like happy or smile might be more valuable than removing them. So I am so happy. Removal of emotions, converting emotion to words, replace emotion like sad and happy. Emotions are old school emotional markers made from punctuation marks like for happiness or for sadness. They are especially common in SMS. emails, chat apps, while they don't use Unicode like emojis, they still convey emotion in this step. We define a dictionary that maps emotions to their meanings. Then we replace any emoticons emotion in text with the corresponding word. This helps NLP models interpret sentiments or emotion explicitly rather than guessing from symbols. Depending on your use case, for sentiment detection, convert emotions to words. For formal processing, you might choose to remove the altogether. Combine handling of emojis and emotions. Emojis and emotion are express emotions. Many users express feeling using both emojis and emotion. For example, this is a graphical emojis. Is a text-based emotions. NLP models often treat them as noise unless we pre-process them. Here is how we handle them together. Emojis to word, emojis dematize, and then into smile clean formatting, regress, remove the turning smile into smile. A custom dictionary replaced smile with sad face. This combined approaches ensure the emotions meaning is preserved and ready for analysis. Removing punctuation and special characters. Punctuation often serves grammatical purpose but adds noise in NLP tasks. Removing it helps consistent tokenization. Reducing vocabulary size, however, in specialized tasks like hashtag or handle analysis, some punctuation may be useful or should be preserved. Hello worlds, let's removing extra white space, replace multiple white space with a single space. Irregular white space often comes from user generated content. Web scraping and merging text fields. Multiple spaces cause issues during tokenization or comparison. Using this, collapse all spacing into a single space while stripping remove leading trailing spaces. So this is space out, no space here. Removing single characters like A, B, X. Single letters often appear in noise text. These boundaries where only one character exists A. This method removes those standalone characters unless they have grammatical meanings, i.e. in English, which should be preserved depending on the context. Make sure to apply further cleaning like extra white space removal after this step for tidy outputs. Big cat. Removal rare words. Removes words that appear only once in the corpus. Rare words, especially those with frequency equal to 1, often add noise rather than value. This could be spelling mistakes, unique identifier, or hyper-specific terms. Removing them reduces overfitting in models and simplifies training. However, this step should be done carefully in domains like medical or legal text, where rare words might carry crucial meanings. Always inspect rare words before removing them automatically. So, apple, apple 3 times, banana 2 times, and grape only 1 times. So we have apple, apple, or banana, banana, and we remove grape. Removing frequent words. Remove only common words that dominate the corpus. Extremely frequent words like the is often dominate specific words can overshadow others. This may contribute little value in distinction topics or sentiment. Removing top and frequent terms focus the analysis on more meaningful vocabulary. We caution not to remove important frequent terms, evaluate word significance contextually. So we again have a apple 2 times, apple 3 times, banana 2 times, and orange only 1 time. So here we have banana and then banana and only 1 time is a orange. Removing stop words, eliminate common words like the, is, a, reduce noise the textual data. Stop words are very common words like the, is, an, etc. They do not contribute much semantic meanings in many natural languages processing tasks. Removing them reduces the dimensionality of the future space. Helps model focus on informating words, may improve performance in classification, clustering, and topic modeling. However, keep in mind context sensitive tasks like machine translation or sentiment analysis. Removing stop word may sometimes result in a loss of important grammatical structures. So we have only simple sentence testing, simple sentence and testing. Final thought, the power of text normalization. Text normalization is standardized textual feature for consistent, accurate NLP analysis. Text normalization transforms messy textual input into a clean, consistent format by applying different techniques like lowercase, punctuation, removal, tokenizations, and many we are just discussed. This process is essential in NLP for reducing noise and improving model accuracy. Clean and standardized text ensure that machine learning models can interpret language data more effectively. Thank you. Proximity measures, and it have similarity measures and dissimilarity measures. Approximator in data analysis. Approximator measures refer to numerical values that quantify how similar two data objects are. It is commonly used in data mining, machine learning, clustering, and information retrieval to evaluate the relationship between items, points, and vectors. There are two main types of proximity measures. First, similarity measures how like two data points are, and which mean high value, greater similarity. For example, two users with very similar movie ratings. Similarity common in recommendation systems, text analysis. This similarity, distance, measures how different two data points are, have lower values, mean greater similarity or dissimilarity. Examples, two users with very different rating on the same movies. This similarity commonly used in clustering nearest neighbors algorithms. Similarity measures, we will discuss cosine similarity. Jacquard similarity, and Pearson correlation.
Similarity, dissimilarity measures in data science. Similarity measures determine how alike two data objects are. Cosine similarity, it means measures the cosine of the angle between two vectors. Jacquard similarity used for binary or set data, intersection over union. Pearson correlation measures linear correlation between two sets of data. The similarity measures is to tell how much the data objects are distinct. They are Euclidean distance, straight line distance including space, Manhattan distance, taxicab or L1 norm, sum of absolute differences, Minkowski distance, generalization of Euclidean and Manhattan, and Hamming distance, numbers of position with different values used in strings. So first we see similarity measures in data science. I have already told cosine, Jacquard and Pearson. In forthcoming slide, I introduce the concept of similarity measures. These measures help us compare data item in a numerical format. Cosine similarity is strictly used with vector in text or recommendation systems. Jacquard with sets with Pearson and numerical data to observe linear patterns. Each has its use cases depending on the nature of data, vector set or continuous values. First, cosine similarity measures. It evaluates similarity by direction, not magnitude. Cosine similarity is a metric used to measure how similar two vectors are based on angles between them. So cosine similarity is 0 minus 1 to 1. 1 means perfectly similar. 0 means no similarity angles, and minus 1 means minus 1 means uh, completely opposite. You can say angle 180. This is its formula, and this is similarity measures in Python, and this is the four lines which we need to evaluate. Document 1, 2, 3, 4, and actually we define the document, and this is the results of all four documents are arrow from the origins. Vector pointing in different direction depending on their textual contents. Angles in degree printed between doc 1 and each of the other doc 2. Doc 1 and doc 2 are semantically similar. Both are about students using a uh, ChatGPT and academic work. Doc 3 is about the weather, and Doc 4 about AI in academic setup. Don't develop overlap which with the rest, especially Doc 3. Jacquard coefficient. It measures the similarity between two sets by comparing their intersection and union. Simply, Jacquard similarity or Jacquard coefficient measures the similarity between two sets. It is calculated as the size of intersection divided by the size of union of the set. Intersection common element in the both union total unique elements from the both sets, and high Jacquard value indicate greater similarity. This is formula. And the real world example is education, correlating study hours and exam scores. In we use economics, whereas economic level and spending behavior. In health, daily sugar intake and blood sugar levels. And that's one. So you can see we have our two users, user one and user two. They went to buy some grocery and they have egg and cheese difference, and then butter and jam. But the common thing is bread and milk. Bread and milk are common, but one user got egg and cheese separate, and the other one is butter and jam. Pearson correlation is about this is a formula. Peer correlation coefficient, also known as Pearson's or simply correlation coefficients, is a measure of the linear relationship between two continuous variables. It tells you how strongly and what in direction two variables are related. So this one about the plus one is a perfect positive relationship. There is a no correlations, and these are the minus one is a negative. Real use case, business marketing spend versus sales, education study hours for academic performance, healthcare blood pressures versus age, and finance income versus expenditure. This one data Python, and we have this one over the studies and exam scores. And this is the results. We can say the more you study hours and the more you spend in the get better results.
These similarity measures, we will discuss Euclidean distance, Manhattan distance, Minkowski distance, and Hamming distance.
Dissimilarity distance measures in data science, Euclidean sum of straight line distance in Euclidean space, Manhattan sum of absolute difference, Minkowski generalization of education and Manhattan, and Hamming number of position with different values used in strings. Euclidean distance dissimilarity, uh, mostly common used for continuous numerical features. Assume features are on the same scale. Euclidean distance is the most commonly used the formula used metric for continuous numerical data. It represents the straight line or as the crow flies distance between 2 points in Euclidean space because it assumes all features contribute equally and are on the same scale. Normalization or standardization of data is often necessary. This metric is foundational in clustering algorithm like k-means and in classification algorithm like k-nearest neighbors. However, its effectiveness can diminish in high dimensional dataset due to the curse of dimensionality where distance become less meaningful. So we have a point 1 2 TD space and for 6 point B, and result will be is the 5. How this one? So they start from the 0 1 and they are a 5 6 until 6. So the result is 5. Manhattan distance, it also known as city block or taxi cab distance, measures how far apart 2 points are if you can only travel horizontal or vertical, like along city streets. It is widely used in urban planning, robotics, and machine learning application where movements is grid based. Formula. This is Python formula and coding about we have a 2 points, 2 and 3 and 7 and 6. So Manhattan distance is each green line segment is counted as one step. either 1 unit right x-axis or 1 unit up y-axis. The number 1 beside each segment shows the count for each unit. 5 steps horizontal from x2 to x7. 3 steps vertical from y3 to 6. The box formula at the top visually proves the computations and the end answer is 8. Minkowski distance. Here, distance is a generalized metric that measures the distance between 2 points in a metric space. It's a flexible measure that encompasses both Euclidean distance R2 or Manhattan distance R1. So the P2 is reduces the Manhattan distance and P2 including distance and AP infinity, it approaches the Chebyshev supreme distance, which considers the maximum coordinate difference. So Manhattan is P1, Euclidean distance P2, and then infinity. Maximum coordinate difference, straight line distance, and grid based Y system. So Python code for figures 2, 3 and 7, 6, and we will measure the Manhattan, Euclidean, Minkowski and Chebyshev, and this is the presentations here. Manhattan distance is like a walking a grid. Think street in Manhattan. You can only move horizontal and vertical. The total distance is 8 point. Euclidean distance P2, this is the straight line as the crow flies. Distance between the 2 points is shorter than Manhattan since it does not follow a grid. Minkowski, the lies between Manhattan Euclidean distance, it is weight larger difference more heavily than Euclidean but not extremely as Chebyshev. Chebyshev is safe distance. The only cares about the larger single coordinate difference. It is like moving a chess as a king. The number of step it takes depends on the further directions. Each bar is the chart show one line distance metric, height of the bar equal to distance values. The Manhattan distance is the highest because it follows the grid. Euclidean distance is the shorter due to diagonal environment. Minkowski is between Euclidean and Manhattan. And the last one is the smallest because the only cares about the single greatest difference. The Hamming distance is a metric used to quantify how different two strings of equal length are. The particular useful in application where exact or near match the required such as data transmission or genetic comparison. So from this one there are two words Carillon distance from here and then the point numbers are here. The difference is there. So visualize them here. You can see each vertical bar shows top red or green. This one character from string A and the bottom below are green character from string B. White label the character is in each positions. This one or you may say this one, and red and blue are mismatch. And x-axis is the character positions. So similarity measures in data science, similarity measure evaluate how alike The two objects are high values indicates more closeness. Common examples. The similarity distance measure evaluate how different two objects are highly value mean more separation. Common examples. Both types help us quantify relationship between the data points. Similarity focus on closeness while distance measures difference. Choice depend on data types and tasks. Thank you.
And distance measures for binary variables.
Distance measures for binary variable. In this context of binary variable, distance measures help quantify the similarity or dissimilarity between two objects based on their attributes, where each attribute is either 0 or 1. Let's break down the core concepts. Types of binary variables. Symmetric binary variable, both 00 and 11 pairs are considered equally important. For example, in identifying whether two objects have the same properties, both are of the same color or both have specific types. Both matches 00 or 11 have equal significance. A symmetric binary variable, only ones are important while zeros are ignored. A good example would be in middle medical test. Let's say when we go for disease presence or purchase behavior, where a positive result 1 is more significant than a negative result 0. If a test result is negative 0, it does not add any value to the distance metric. So you see here, A is 1 and B is 0. The type is 1 0 mismatch. 0 1 or 0 1 type is mismatch, and 1 1 or 0 0 is match. This is we need to found symmetric and a symmetric distance variable, and here you can see the symmetric variable is distance f01 and f10 from here, and then we have a mismatch because 2 plus 2 is equal to 4, and 4 divided by 6 as per the formula, this formula, and the result is 4 out of 6 features are mismatched. Similarly, in symmetric, we say f01 and f10 and divide by Jaccard dominators. The result will be 4 by 5 and equal is 0 0.8. Continue for Python code, and here we can see the display the result in the next slide. So we already told you 0.667 is symmetric and distance is symmetric 0.8. So here we match here because we have 0 1 0 1 1 0 1 0 1 0 in A, and the B is 0 1 1 0 0 1. So these are the B, A, and the B is 0 0 1 1 and 0. So we can say those are mismatch and match.
Coherence.
So coherence is measures of how well a group of items such as terms, documents, or feature semantically or statistically go together. Coherence answer a simple but crucial question. Do these terms belong together logically? While data science models group things based on numbers, coherence ensure that those grouping make a real world sense. This is especially important in NLP, where we deal with words and meanings. Think of coherence as the bridge between statistics and semantics. It helps ensure our models are not just mathematically correct but also meaningful and interpretable. Concept is simple topic modeling like LDA to evaluate the quality of generated topics. Think of coherence like quality control test for grouping. In topic modeling, it tells us whether the top words in a topic are actually related. Clustering to assess how well data points within the same cluster relates. In clustering, it tells us whether the items within a group actually share common characteristics. Recommendation systems NLP to ensure generated associations make logical sense. In recommendation systems, coherence ensures that suggestions make contextual sense, like recommending books to the same genre, not just a random popular item. Overall, coherence gives us a way to validate that our grouping feel right. Coherence in a topic modeling, NLP. High coherence words are semantically related, like data, model, learning. Low coherence words are unrelated, like car, banana, algorithm. Metric example C under root V coherence words coherence. In topic modeling, we often ask, are these topics useful? Coherence helps us answer that. If you see a topic with words like data, model, and learning, you instantly get it. That's high coherence. But if you say banana, stock, and algorithm, it's just confusing. Types of coherence measures computed using word occurrence statistics and civic underscore coherence combine NP MI normalize point-wise mutual information and cosine similarity with a sliding window. It is a very popular because it combines multiple insights. How often words appear together and how similar they are vector wise. U underscore mesh coherence. Based on document coherence count needs a reference corpus. It is simpler but depends on having a good corpus. Use point-wise mutual information PMI between words pair. Focus on PMI which checks if words appear together more than you would expect by chance. What are we trying to do? Our goal is to check whether the topic we create from documents are good and understandable. We use a coherence score to tell us what the machine thinks is a good topic and compare it with real students say that they understand that. So we can compare a machine evaluated topic quality with the student feedbacks, etc. Measuring coherence measures topic quality based on actual usage in the document, and the score range is from 0 to 1. Higher is equal to better. This model looks at each topic and see if the words usually occur together in our documents. If they do, the topic gets a high score. Think of it like checking if machines and learning always show up as a team. Simulating students' feedback, given student understanding score, few topic equal to less clarity, and too many topics, obviously confusing, peak understanding around 3 topics. We pretend we ask a student how well they understand the material. Their score increase until they hit their comfort zone. Three topics, then drop when there are too many topics to process. So in forthcoming Python code, we have the documents. We have four simple documents: data science, machine learning, and blah blah. So there are four input documents. Each one is short list of words. They belong to a specific themes. They are like notes written with the different students. So this is the documents, and these are the create topics with the keywords. Instead of letting a model find the topics, we define them ourselves. We assume these word pairs make sense together. Now we will see how these topics hold up when evaluated. So code this one and this one, and then continue code, and this is a comparison. And blue line is a coherence score, and green dash line is students understanding, and x-axis is number of topics plus their keywords. Excuse me. The plot helps us compare what the machine says about coherence and what students say understanding. We look for their both lines are high. That's our sweet top spot. So number one is too vague. Number two, if we go there, uh, better but still bored. Sweet topics, topics make sense and easy to understand. And the four is okay, but maybe too much details. And topic five are clear but could feel overwhelming.
Data binning.
Data binning is technique convert continuous data into categorical data by grouping values into predefined bins. This process simplifies data and reduce noise, making it easier to work. Data binning is an essential pre-processing technique that converts continuous numerical data into categories, simplifying analysis and trend identification. It is particularly useful for large data sets where excessive noise can obscure pattern. By grouping similar values, binning enhances interpretability and improves model performance. Why use data binnings? Noise reductions. Binning can help reduce the effects of outlier and noisy data. By grouping similar values together, it smooths the data and helps to highlight the main trends. Improved algorithm performance for some machine learning algorithm like decision tree and histograms, data binning can lead to more effective and stable results. These algorithms often perform better when data is categorized into manageable range. Simplifies analysis. Instead of dealing with exact data values, binning allow us to work with range or groups. This makes it easier to interpret and work with large data set. Types of data binning. Equal with binning divide the full range of values into equal size intervals. Equal frequency binning. Each bin has approximately the same number of data points. Other binning techniques, binning by mean, replace all values in a bin with the average mean of that bin. Binning by boundaries, replace values with the nearest bin edge. Equal with binning, data binning divide the full range of value into equal size interval. So Python code. Equal with binning is like a slicing a ruler into equal segments. No matter where the data lies, the bins are all the same size. This helps simplifies analysis, but it can sometimes lead to empty or uneven bins of the data isn't spread out evenly. The color in the chart helps students visually connect each number with its bin. So the range was a minimum and maximum. There is a 26, 30. Maximum was 30 and minimum is 4, so equal to 26. And then width divided by 26 into by 3, so equal is 8.67. So these are, we can say, first bin, second bin, and it is a third bin. And this is a third bin. The binning is calculated by dividing the full range of values into three equal segments. Each value is slotted into the bin whose range it fall into. So this one, the values, right? The minimum is 4 and maximum is 30. Equal frequency binning data bins. Each bin has approximately the same number of data points. Uh, we group beyond regular binning. Not only we grouping values into bins, we are replacing all value in a bin with the bin's average. This technique smoother noisy data, and it is often used in data cleaning and preparation. So what does the code do? Generate, we will generate 100 values, divide them into three equal bins, and replace value in each bin with the bin's average, and visualize the original and modified values. We are working with the randomly generated data to simulate real world data set. After binning, we calculate the mean of each bin and replace all the values in that bin with the means. Finally, we plot both the original and modified data for comparison. So we have a normal distribution of the 100 points and multiply by 10 to increase the range, and value range is minus 30 to 30. We simulate data set of 100 values with the bell-shaped distribution spread wider by multiplying with 10. This gave us realistic variable. The code the code takes a list of number values divided into four bins, where each bin contain an equal numbers of values are close as possible. It then displays how each value is grouped and visualized with the color coded bar chart. The queue, this one, functions from pandas splits data into bins where each bin has almost for the same number of values. It is different form of equal with binning with focus on ranges. And this is the original data. And we can see there are four bins, the same number, and now we have a four bins. Other binning techniques, binning by means, replace all values in a bin with the average mean of that bin. Instead of keeping the original numbers, we replace each value in a bin with the average of that bin. The smooths that data. Binning by boundaries, replace values with the nearest bin edge. We replace each value with the nearest bin edge. So if a value is closer to the lower edge, we replace it with that. Both of these are helpful for reducing tiny variation that might not be important to the overall trend but could confuse our models. Binning by mid Python code. Continue code. And winning by mean, what did the code do? We took 100 random values like exam score, temperature readings, etc., and grouped them into three equal with bins, like splitting a class into three score ranges. Then for each group or bin, we calculated the average mean for all values in that bin, replace the original values with that average only for visualization. This plot teaches students how binning work as a smooth techniques. The original data shown in a teal color. This contains random fluctuation by grouping the data into three bins based on a range and replacing each group with the mean values. This the chart becomes smoother and easier to interpret. The purple line with, is 1, 2, and 3. The purple line, vertical lines indicate the states and the end of each bins, helping students visualize the boundaries. This method is useful, removing outlier and making pattern more visible. Binning by boundary, code, continue code, code, and this one is the results. Original data, first the data is split into three equals. Range, also called bins. Each data point is then shaped into the closest bin boundary, either the lower or upper range. The method is useful. We want to reduce noise in the data while preserving general trend. 1, 2, and 3. So data binning is a powerful tool for simplifying continuous data, especially in machine learning tasks. It helps reduce the complexity of working with noisy continuous data by categorizing it into the bins that we are easier to analyze. Try experimenting with different binning techniques, equal width, equal frequency, mean or boundary, to see how they affect your data analysis and model performance.
These methods not only prepare data for machine learning but also help uncover pattern, reduce noise, and improve interpretability. As we move forward, keep these tools in your pre-processing toolkit. They are fundamental for building robust and insight models. That brings us to end of part 3 on data pre-processing. Today we cover essential technique that form the backbone of any data-driven workflow. Thank you for your attention and see you in next session.